going to show you the sys traces, and I'm going to show you how to spot issues. Issues that we found aplenty, of course, but 4 were most widespread. I would say that these 4 performance pitfalls were basically every game I saw had 1, 2, or 3 of them. I just found myself saying the same thing over and over again. I said, let's look at I/O to a bunch of other people, so I don't have to repeat myself all the time. I'm going to go in depth on each one of them. I'm going to show you sys traces and how to spot it in your game. That's the first one. And this is sys trace. This is basically a certain number of cores, 8 in this case. And you can see all the threads running in the system. And you can see this thread number 3, which is basically grabbing 1 core. 2 is jumping from one to the other, but essentially it's grabbing 1 core and hammering it, while the rest of the system does nothing. That's how a single-threaded game looks in sys trace. And that is OK in the sense that if you're making a casual game, a single-threaded casual game is the right thing to do. I get it. It's just much easier. The architecture is easier. Everything is simpler. You don't have to look at synchronization. I get it. It's a simple thing to do. But if you're pushing the boundaries a little bit more, well, you have 8 cores. You're using 1. It's a matter of performance, but as we're going to see later, it's not only about performance. This is an example of a Unity game. I'm not going to ask you how many Unity developers are here. It's like everyone asks the same question. But I believe there are going to be many. There's going to be a Unity main thread, single thread, hammering a system, just 1 core. Everything else does nothing. That's how it typically looks like in Unity. And that's actually very, very simple to fix. That's it. Click, 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 click that thing. Multi-thread rendering, that one. Here, just click it. It's going to make your game run faster and be better. It will make me happier. Since you're there, you click GPU skinning as well, because you don't want to skin on the CPU. It's bad, and it makes me cry. I don't have a picture for that, but imagine it. Once you click that, that's how your system is going to look. There's going to be a nice main thread, which is processing entity. Each entity will generate a bunch of graphics commands for a render thread that will take this graphics command, and in parallel, it will generate a bunch of rendering commands for the GPU, which runs in parallel. Now, instead of having a thread that is hammering 1 core, you have 2 threads. At least you're parallelizing your work. And that's how sys trace is going to look like. You're going to have Unity main, it's a little bit smaller. Unity GFX device. I don't know why W. I always wondered why. This is not going to give you a double frame rate straight out of the gate, because you're not probably going to have workloads that are exactly the same time and can be just perfectly parallelized. But I mean, you see, it's a pretty decent difference. You're going to get something out of it. More interestingly, you're going to let the CPU that is running Unity main have the chance to sleep for a little bit. We'll see why it's very, very important to let cores sleep. Sounds weird. At the end of the day, you want to parallelize your workloads, because they will give you better performance, but also because if you don't do that, that's what happens. Higher power consumption. That's a direct consequence of having 1 single thread that does everything. It means that you're going to consume more power, you're going to drain the battery much faster, which leads us to the second issue. This is a gigantic deal. This is a big deal. If there is one thing that I need you to remember out of here is thermal throttling is a big deal. That's because on mobile, performance is not constant over time. Here's the thing. I worked on console and PC. Better on console. It's more fun. But once I made my frame take 33 milliseconds to process, I was done. I lived in England at the time. Everyone was going to the pub. I'm Italian. I was having a coffee. Please don't have cappuccino after lunch. It's bad. On mobile, things are much different. On mobile, once you render 33 milliseconds for a frame, here's what happens. You have your carefully optimized game. You give it to someone to play. It looks great. It runs beautifully for 10 minutes. And then this device is going to get hot. Device getting hot means performance will go down because phones that explode generally are not perceived well by clients. So manufacturers have to slow things down so the device can cool down. So your game that was running at 30 frames per second on the clock now is running at 20, 15, 10. And your customer will go and play and write you a one-star review. One-star reviews are bad. I have an equation on my slide. I know math. Look at that. Power consumption for a CPU is equal to capacitance thingy, C, that thing, as a constant of some sort, multiplied by square of the voltage, multiplied by its frequency. Now, in systrace, you can see for each core the frequency, like values like 2 gigahertz, I think. And you can see that thread 3 is basically maxing out frequency on that core. Also, in order to run at max frequency, the voltage has to go up as well to maintain the tight timings in the transistors. At least that's what they told me at the university 25 years ago. But also, notice this very interesting phenomenon. The frequency at some point goes down because the scheduler decided to lower the frequency. But each core goes down at the same time. You can say like 1, 2, 3, 4 times in a row. They all go down at the same time. That means that by virtue of having thread 3 maxing out frequency on one of the cores and maxing out voltage on one of the cores, voltage is squared, just like it's consuming a lot of power, it's forcing that small thread, N, to consume a lot of power for a little bit of work that most probably doesn't need to run fast. If that thing takes 10 times to run, you will still hit 30 frames per second, most probably. This phenomenon is clearer here. This is a Snapdragon 855. Yep, if I remember correctly. This has 2.5 clusters of cores. The small ones that run at a lower clock. Clock 2, 3 cores that run a higher clock, and there's another one, clock 3, that runs at even higher clock. So basically, each cluster has a clock plane, and each cluster is voltage gated. That means that each cluster runs at the same voltage and the same clock frequency. Except for clock 3 that can run a different frequency from clock 2. Interestingly, even if it runs a different frequency from clock 2, they still share the same voltage. Which means if the voltage goes up for the last CPU, 3 more CPUs go up, everything consumes a lot of power to run. Big takeaway here, cores in a cluster always share the same clock. This doesn't make me happy because it makes my life harder, and yours as well. On the other hand, it's much simpler to design, and it's understandable why all SoCs are designed this way. No exception whatsoever. This is another example. This is very interesting because CPU 0, 1, 2, and 3 are little cores. 4, 5, 6, and 7 are big cores. Now, every SoC I've ever seen has the first cores as little cores with smaller caches, lower frequencies, and the last 4 cores, big cores, or even bigger, with larger caches, higher frequency, much faster, and much more power hungry. They all look the same, but please still do your due diligence and try to understand the topology of the SoC programmatically. There are ways to do it, and we can talk about it later in the game reviews if you come over. Look at that W. This is another Unity game. W is a worker thread. All these worker threads are running on CPU 4, 5, 6, and 7, and little cores are doing nothing effectively. These could be running on the little cores, consume much less power, and give the big cores more chances to go to sleep. Going to sleep means no power consumed. It means lower temperature in general, less chances to throttle, less chances to go into thermal throttle, less chances to get the device hot. Because all phones, sooner or later, will overheat and will be throttled. And that's not under your control. You will not be told why. You will not be told when. Every device is different. Every manufacturer has its own secret sauce on how to do it. It depends on the environment. I mean, if you play in Finland, you can probably play for a while. If you play in Italy, nope, it's hot. In summer, especially. You have to do everything in your power, which means ship as much as possible to be executed on little cores in order to avoid thermal throttling. At the end of the day, distributor workloads, which is very similar from parallelize your workloads. Going multi-threaded will help you with thermal throttling as well. Which workload you want to run where? Well, here's the thing. High memory bandwidth, you're reading a lot from the system memory, or you need a lot of cache to go fast. Well, this kind of workload goes well on a big core. You're doing a lot of math. Well, lots of math means big core again, because big cores have the math instructions. Little cores don't, so they're much slower. Everything else, just send it to the little cores and make me happy. This is an interesting statistic. Well, it's not statistics, it's numbers. On a Pixel 3, a little core consumes 31 milliampere. Big core, 215. It's a 7 times ratio, which means that if you have a piece of work that you move to a little core, if that piece of work takes less than 7 times the time to run when compared to the big core, you're saving power. As long as you run at 30 frames per second, you're good. That's the kind of memory model that you have to think about. On the latest devices, this ratio goes up to 20. Like, it's 20 times more power hungry, and it's highly unlikely that you're going to see workload that runs 20 times faster on little core. Just keep it in mind. Look at the audio thread. Well, little cores are doing nothing. That goes straight into a CPU 0, 1, 2, or 3. And this is how you do it. Set affinity. It's just a system call. It's pretty straightforward. This is some code that I wrote. I can claim I'm a programmer now. And it just runs a system call and checks for errors. This is like super straightforward. And this is how you use it. If I want to run on a little core, I set the mask to the first course. If I want to run to the big course, I set the mask to the last course. And then I set the thread affinity. Super straightforward. Just do not pin a thread to a certain core. Just leave some room for the scheduler to do its work, because it's good. But pin it to certain clusters. And now we have, how are we doing time? Ooh, we have 20 minutes left. I have a volunteer here. And I have my camera. This has never been done before at Google I/O. Please, 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 please. Please come in. I just volunteer you. And I'm going to take photos of him. This has never been, please be serious. Like, do a more developer-like face, like a serious one. More serious. A little bit less serious. Look at me. Look at me. Excellent. Excellent. Look awesome. Smile. Excellent. Thank you very much. Did I lose the... Did I lose the thing? The clicker thing? Did I give you the clicking thing? Do you have a clicking thing? It's gone. It's amazing. I don't know. It's gone. Sorry? No, it's gone. Literally disappeared. But we have another one. Frame pacing. Frame pacing is a lot about performance. And in systrace, you have this view which basically shows you where Android is latching on your frame and displaying it. There's basically a very good proxy for when my frame is going to be on screen, when my user is going to be seeing my image. And if you see bars that are not evenly spaced, like sometimes shorter, sometimes bigger, that is sure sign you're having frame pacing issues. This gets a little bit more complicated. Like the first bar up there is when your game is done with the frame and is presenting it to the system so it can be grabbed and be displayed. The second bar is a nice vsync coming every 16.6 milliseconds, 60 frames per second. Down there is the bar that we saw before, just a little bit enlarged. It shows you like the system is doing something, is sending the frame to the hardware compositor, is doing some work. But the point is that at some point when the frame is present in the queue, Android will decide, OK, I got a frame, off it goes to screen. And it took about 50 milliseconds in the first instance, because look at the big circle there. We missed the vsync. We arrived slightly too late with the vsync. So Android had nothing to display. Then when there was something to display, Android was doing its work. Immediately after, the game is presenting another frame. So this is a typical example of a game presenting as fast as possible. And then immediately later, Android says, great, I got the frame. Off it goes to screen, 16 milliseconds later. This translates when you're playing into, I'm running at 20 frames per second, and then I'm running at 60, and then 20, and then 60. So the user perceived this as choppy frame rate. It's a choppy 60 frames per second. One-star review straight away. It's very disturbing. Generally speaking, a 60 frame per second game that is choppy is much worse than a stable 30 frames per second that is nice and smooth. And that's how you see it on systrace. But let's enlarge this one. I'm slightly enlarging it's the same thing that we showed before. I'm just showing you also the CPU. And we can see that this frame, which is like the big bar, started a couple of milliseconds too late after the vsync, and it literally missed by 100 microseconds. It arrived slightly late by 100 microseconds. So Android will present this frame 60 milliseconds too late, because we missed by 100 microseconds. We missed because we started slightly too late. Theoretically, this thread would take less than 33 milliseconds to process the frame. This could run at 30 frames per second, no problem whatsoever. But it's not. And it's not because the game is too slow. It's because it's missing the frame pacing. This is basically the cause of most frame instabilities that I've seen. Because as a game developer, you know that if you want to hit 30 frames per second, you have to run a frame in less than 33 milliseconds. Most people do it because they're good. But then they don't present it at the right time, and the frame rate is still choppy, and you have frame time stability. But not only. Another issue is, imagine a touch input that comes when the first frame that takes 50 milliseconds to be displayed. Well, this is going to be showed 60 milliseconds later. So I touch, and I see the result of my touch 60 milliseconds too late, and then I see the result of my touch in the next frame like 60 milliseconds too early, and this goes back and forth. The brain is trained to expect input at a certain cadence. If we just keep going back and forth, it's a bad experience. We do have a solution. It's called Android Frame Pacing API. Tian mentioned it before. This is a bunch of code that doesn't live inside Android. It lives as a library. And you can download it and try it. It supports several case scenarios, and it's very easy to integrate. And basically what it does is there's an init, there's a swap, and there's a set a bunch of parameters. And from there on, it will take care of making sure that your frame is nicely presented right before the vsync. And also it will give you back callbacks that you can use to start your game logic right on time at the vsync. You put the two things together, as long as you're running in less than 30 milliseconds, 33, you're good. You will be frame paced perfectly at 30 frames per second. And that's all done by us. You don't have to care about what kind of devices, because devices are slightly different in the way they treat the vsync and they treat the latching. You just don't have to care about it. Set your frame interval as you're used to, and off it goes. It's available for both Vulkan and OpenGL. This is the Vulkan Virtue. It's init, set a swap interval, and then at some point in the future, swap. When you swap, swap will return, and it will be presented. And then you will have a callback, and you can start your game logic straight away at the next vsync. It also comes with auto mode, which is kind of a peculiar mode to run in. There are situations where, imagine your game is running on a device that is not as performant. So it mostly hits 30 frames per second, but sometimes it slows down on a heavy scene and runs at 20 frames per second. Well, in the case that we just saw earlier, well, a frame will come at 50 frames per second, then the second one will probably be at 16, because I arrived slightly late, but then I present another one. Maybe it's going to be at 33. I don't know. It's going to be as fast as possible, but the frame rate will be choppy. Auto mode detects this condition and says, good, you're running at a stable 20. You're not hitting a stable 30. Well, I'm going to slow you down for the time being. You can reset at any time, but when the frame rate goes back to a more stable 30 frames per second, auto mode will bump you up again. It has the very good consequence that you're also going to save battery, because it will take certain frames and will just slow them down, just introduce waitings, which means CPUs and GPUs will have more chances to go to sleep. That's how 30 frames per second looks like. This is a stable pacing. Now, if you come over there, we can show you the frame pacing API on one of the devices. And we can go more in depth. Last but not least, this is a fun one, because you have phones that are packed with 4 megapixels today. And many games make sure that they're going to shade each megapixel, each pixel in the megapixel. 4 megapixel, for reference, is twice, give or take, a full HD resolution, which probably a year ago was state-of-the-art console-like rendering sent to a 55-inch display, and it was like, awesome, this is a great-looking game, it runs a full HD. When I was working on console, I was running a 720. 720 is 1 megapixel. Now phones, we have 4 megapixel packed there. You do not need to shade all of them. Please don't. Because that's how I feel about it. How do you recognize that you are probably shading too many pixels? Well, you're going to be GPU bound, likely. In systrace, there is a bar that gives you the buffer count. Buffer count means that the CPU is presenting a frame. Buffer count goes to 1. The GPU does its own thing, just shade every single pixel. Then the CPU is doing its work for the next frame. And if the GPU hasn't finished yet, well, the CPU will just put another buffer in the queue, just ready, good to go. And then wait, most probably. And the GPU will just try to catch up. Well, that's a situation where this buffer count goes back to 2. Another way of saying it is, well, I have a frame that is presented in 50 milliseconds. Let's assume we don't have any frame pacing issue here. We already solved it. Well, but my frame time is taking 40 milliseconds. Where the rest of the time is spent, most probably, is going to be spent shading all 4 megapixels. This is very straightforward to find out in systraces. I've seen a bunch looking exactly like this. Now, here's how you solve it. Instead of a 3K by 1440 display, instead of rendering to all of it, well, create a render target that is smaller and make sure that you only stretch in one direction. Reason is, when you interpolate back, it's going to be much higher quality and much more cache friendliness help. And make sure that you're only rendering your game word into this smaller render target, not the UI. The UI has generally thin things and thin lines and fonts. They don't scale well, just rendering in full resolution. UIs, except for some cases, tend not to be too heavy, so they can go at full resolution, and then composite the two. In this case, you're saving 58% of the pixels. This is going to be roughly a full HD, still on a smaller screen. It's going to look amazing. It's going to look great. Nobody's going to see it. If your artists think that they're going to see the difference, just tell them that they won't. If they still insist, use my trick. I never told artists that I was doing any of these optimizations, and they never spotted me. That's why I'm still here. If they spotted me, I probably wouldn't. My artists were awfully mean. To do the resize, it costs some time. It costs some GPU time because you have to interpolate back to full screen for the final presentation and final compositing. And every Android device has a hardware composer that is not exposed to the user, which doesn't make me particularly happy. On the other hand, any game that would probably use this kind of techniques and would probably be GPU bound has some kind of post-processing and tone mapping at the end, where you're doing, I don't know, some kind of blooming, some kind of color correction. Well, you can do the process of stretching back to full resolution in the post-processing step. It comes out not for free, because nothing is free, but it's a nice way to hide the time and to use it for something useful. This is a pretty common way of doing the stretching back. The important thing, and I want to stress this point, is that please stretch only in one direction. Do not resize in two directions. The quality is much higher if you do it in one direction. We've seen these 4 big, I would say, performance pitfalls. And I showed you various ways to tackle it. Now you have a better knowledge of what you can encounter in the field and a better knowledge of how to solve these issues. They're pretty easy at the end of the day, except probably the last one. Like, it doesn't take long to implement it. And use this knowledge. Now, please go out there and make some great games. My name is Francesco Carucci.